So in this video, I will present a few features of the complex numbers, mainly connected to complex multiplication. I will assume that you're familiar with some of the basics of complex numbers, such as the real and the imaginary part, the modulus and the argument, and also addition on the complex numbers. Sometimes people feel a little bit uncomfortable when they first encounter complex numbers. Maybe that's due to the terminology used, like complex and imaginary, or maybe it's because that the complex numbers are not lined up nicely on the real line, like all the other numbers we are used to, like the integers or the real numbers. But once we accept the fact that complex numbers can't be lined up in any reasonable way, and that each point on the complex plane simply represents a complex number which has a real part we usually call x and an imaginary part which we usually call y, and we write it as x plus iy, then we can work with the complex numbers just like with any other numbers. And in fact, it turns out that complex numbers have in many respects much nicer features and often reveal much more about a mathematical problem than the real numbers do. And I hope you will see that in the course of this video. So when multiplying two complex numbers, it's actually very useful to move to polar coordinates, and which means that we think of a complex number, let's say z here, in terms of its argument, which is the angle with the x-axis, often named theta, and its modulus, often named r. And this complex number z we can then write by Euler's formula as r times e to the I theta. And if you would want to relate this to the real and imaginary part, this would be r times cosine theta plus I sine theta. Okay, so if you take two complex numbers, z1 and z2, z1 with argument theta 1 and modulus r1, and z2 with argument theta 2 and modulus r2, then the product of z1 and z2 is simply r1 times r2. And since we multiply these two terms by adding the exponents, what we get is this expression. And what you see is that multiplying these two complex numbers really amounts to multiplying the two moduli and adding the two arguments. So keep that in mind, please. So again, multiplying two complex numbers amounts to multiplying their moduli and adding their angles together. So the first example I would like to discuss in this context is the following. Let's suppose you need to compute 1 plus I to the power 16, which looks quite a difficult problem, and if you would want to do this algebraically, it would be a lot of computation. Now, let's look at this as a geometric problem. So the complex number 1 plus I is somewhere around here with coordinates 1, 1. It has an argument of pi over 4, and its modulus is square root of 2. So raising a number to the power 16 is nothing else than multiplying this number by itself 16 times. So that means if we multiply this complex number by itself 16 times, means we need to add on its angle 16 times to itself. So pi over 4 added on to itself is pi over 2. And you see we move around the circle here, each time adding on the angle pi over 4. And you realize that after 8 times, we are once around the circle, and we do it another 8 times, we move once more around the circle and we land on the real line. So that means the result here, the answer, will be a real number lying somewhere on the real line. Now, how far out will this number lie? Well, we have to take the modulus of this number, square root of 2, and multiply it by itself 16 times. That means raise square root of 2 to the power 16, which is the same as 2 to the 8, which is 256. So without any computation apart from this little one, we can right away write down the answer, namely 1 plus I to the power 16 is the real number 256, which I can't draw because it's very, very far out there. Now, of course, you could have done this also using the Euler formula here, namely by writing 1 plus I to the power 16 in this form, namely as square root of 2 times e to the I pi over 4, and this whole expression to the power 16, and that comes out as square root of 2 to the 16, and this here comes in here as I times 16 times pi over 4, which is 4 pi. So we know the first part is 256, and since 4 pi is the same angle as the angle naught, this becomes e to the 0, which is just 1, and that's our result. But I think it's a very good way of thinking about what happens here geometrically as you multiply these complex numbers together. The second example I would like to discuss in this context is connected with finding roots. So the problem is to find all solutions of the equation z to the 5 equals 1. So finding the solutions to this equation is the same as finding what's referred to as the roots of unity. Here 1 being the unity, and we're really finding the roots of 1. So again, I want to look at this problem as a geometric problem. So I'll draw the complex plane, and we can see right away that the number 1 is actually a solution to this equation. So I record this as my first solution, z1 equals 1. The next thing to notice is that all the solutions to this equation lie on the unit circle. In other words, the circle with radius 1. I'll draw it. And so why is that? Well, if a solution would lie out here, as I raise such a number to the power 5, its modulus would grow, and it could never be, its fifth power could never have modulus 1. If the number were to lie inside the circle, as I raise it to the power 5, its modulus would decrease and could never have modulus 1 when I get to the fifth power. So the solutions have to lie on this unit circle. Now, at what angle do these solutions have to lie? Well, raising this number to the power 5 means adding the angle on 5 times, and after 5 steps, I need to land at the number 1 here, and I need to have gone once around the circle. So it's quite clear that the number must lie at angle 2 pi over 5. 2 pi being the full circle, and this being divided into 5 pieces. So that's about here. So that's 2 pi over 5. Now, as I multiply, let's call this solution z2. This is e to the I 2 pi over 5. When I look at z2 squared, I will be about here. z2 cubed will be about over here. And z2 to the 4 will be somewhere over here. So as I multiply this number by itself, I walk here around the circle in steps of angles 2 pi over 5 until I land at 1. So this is my second solution, and I'm claiming that each of these points are also solutions. So if I look here, for example, at Z3, if I multiply Z3 by itself, what I do is I always jump 2 steps. So Z3, jump over here, jump over here, jump over here, and come back to 1. So I go twice around the circle. If I start with this point, I would go 3 times around the circle, and so on. So each of these complex numbers is a solution to this equation. So now I can easily list them. So Z1 is equal to 1, Z2 is equal to I 2 pi over 5th, Z3 is EI 4 pi over 5th. So each time I just add on the angle 2 pi over 5th. Z4 equals e to the I 6 pi over 5. And the last one, there are 5 solutions, which I expect to get in this case, is e to the I 8 pi over 5. Okay, so this solves the problem, but it's probably worthwhile noting another fact that comes out of this problem, namely, since it's quite easy to factorize this polynomial, not fully factorize, but take out one factor, z minus 1, which has the solution 1 times z to the 4 plus z to the 3 plus z squared plus z plus 1. So 1 is a solution to this factor. The other 4 solutions, z2 through z5, are actually solutions to the equation z to the 4 plus z cubed plus z squared plus z plus 1 equals 0. So that's something that comes out of it. So we have that z2, z3, z4, and z5 are solutions of z to the 4 plus z cubed plus z squared plus z plus 1 equal to 0. It's just sort of an additional fact we get out of this.